Hi everyone. Thanks for who joining who able to join live today, and those who will be watching this recording session afterwards. Welcome to Multimodal Weekly. This is a virtual webinar series hosted by the team at TwelveLabs. We are an early stage company focused on video understanding, and we're meeting on a weekly basis over the past almost 2 years or so. Here are some of the topics that we tend to cover on a weekly basis. Invite a lot of, especially on the research side, we have a lot of researchers come in and talk about their respective research in the domain of multimodal AI and foundation models. Oftentimes we have community members from our Discord sharing their projects that they have built, applications that's built in the past. And obviously we have customers and partners come in and talk about innovative application of multimodal different verticals. And finally, occasionally we have team members talk about how to use a platform and API. Here's some samples of some of the recent session. It's been mostly focused more on like the research side of thing. A couple of weeks ago, we also have like a partner application use cases talking about spot auto highlight generation. So for today's session, we're excited to have the team from Vespa come in to talk about advanced video retrieval at scale using Vespa and TwelveLabs. So for those of you who are not familiar, Vespa is one of our partners. We have been working on a couple of tutorials, content over the past few months, and super excited today to have them come and dive into some more details on the company, the product, custom use cases, as well as the live demo of the integration walkthrough. So for the first half of the talk, we'll have Bonnie Chase, who's currently the Director of Product Marketing at Vespa. She helped drive the go-to-market strategy for a scalable solution that drive real impacts. She had over 2 decades of experience spanning knowledge management, product management, and product marketing. So overall, she's very passionate about bridging the gap between technical innovation and practical business application. And then for the second half of the webinar, we have Zohar Nissare-Houssen, who currently serves as a Presales Lead Engineer at Vespa. He's based out of Toronto in Canada. With over 20 years in data and analytics, he has built a diverse career spanning advanced support, engineering, and pre-sales role at very well-known companies such as IBM, Hortonworks, and Snowflake. So recognizing the importance of multimodal search with high-quality retrieval as one of the fundamentals to effective AI application. Zohar has joined Vespa, I think, just last October, so probably like 6 months, right, with the company now, where you advise customer and partners to implement advanced search, personalization, and AI solution. And so Zohar actually built out the whole tutorials that we'll see today, or that you guys will see in the webinar today on multi-vector video retrieval between Vespa and TwelveLabs. So yeah, I'm super excited to have a run to take a look and ask questions with that. For the attendees, feel free to send your question on the Zoom chat, and then after Bonnie and Zohar finish, we'll have an interactive 10-15 minutes Q&A session towards the end. So I will stop sharing my screen, and I'll pass it to, let me unmute Bonnie. You can share your screen and go ahead with the talk.
Yes, thank you so much. I'll go ahead and share my screen now. All right, great. Well, hello everyone. Thank you so much for joining us. For today's webinar, really excited to share more details about how you can do advanced video retrieval at scale using Vespa and TwelveLabs. So as James mentioned, I'll start by taking a few minutes to give an overview of Vespa and some of those key features that really enable advanced video retrieval. Then Zohar will walk through some of the more technical details on how that's done, followed by a demo at the end. So let's dig in. Now, for those of you who aren't familiar with Vespa, we are a platform for building and running real-time AI applications. And this includes anything from RAG and agentic AI to recommendations and hyper-personalization. And when you look at the search landscape, you have those platform players like Elasticsearch who come from text origins and have some hybrid capabilities. And then you also have these up and coming vector databases. And Vespa really overlaps the two. So you can think of it as more than just a search engine. It's a real-time production grade platform for retrieval, ranking, and inference at scale. And we've actually been working with vectors since 2014. Now, while Vespa spun out of Yahoo at the end of 2023, became a startup, the platform itself has been around for over a decade. And it's been powering mission critical use cases for some of the world's largest and most innovative companies. So, looking at Spotify, Perplexity, Yahoo. So really, using large scale, high demand, hyper personalization. And when we think about some of these use cases, I'll just walk through a few example use cases here. So, obviously co-pilots and assistants are really popular right now. And, the way that Vespa is able to support those is really enabling them to search massive amounts of information and always delivering the most relevant, up-to-date, and contextual answers in real time. It has the ability to search across structured and unstructured data. So whether it's web pages, PDFs, spreadsheets, images, video, audio, Vespa really truly supports multimodal retrieval and ranking. And so this means that users can search and discover insights across any data type, not just text. Mentioned on the slide is LLM caching. So this is, partly to reduce latency and cost, but, you can use Vespa to cache LLM responses such as frequently asked questions in a support chatbot. And this really allows for instant delivery without repeated expensive calls to a language model. When it comes to content classification and safeguarding, Vespa is also used to automatically classify sensitive or risky content. So think about detecting confidential data, hate speech, or policy violations. So really enabling the safer platforms and compliant operations. And then, of course, getting into recommender systems and personalized search. And this is anything from e-commerce to streaming services. And, Vespa is able to power the real-time personalized experiences. So this is, allowing businesses to surface the right product, content, or offers based on user behavior, context, and preferences. So these are all complex, high-scale problems, and Vespa can help make it possible to achieve this by combining the high-performance retrieval, real-time ranking, and flexible machine learning integration all into one platform. So as we think through, how we're able to deliver a high quality, advanced, multimodal retrieval experience, with Vespa, it really starts with the architecture. So I'm going to talk a little bit about how Vespa is able to scale through its distributed architecture. Now, obviously, processing massive amounts of data with low latency is not easy, and it takes more than just fast hardware. It requires really a fundamentally different systems architecture. Now, traditional systems typically follow the same pattern where data is stored in one place and then processing happens somewhere else. So typically a compute cluster. Now, that setup might work for small scale workloads, but it does end up breaking down at scale. And this is because moving large volumes of data over the network can be slow, and the gap between processing speed and network bandwidth keeps getting wider. So Vespa takes a different approach, and this is really about bringing the computation to the data. So with Vespa, data, indices, machine learned models, they're all co-located on the same physical nodes, which means that ranking, filtering, or embedding comparisons can happen locally. And this is without those expensive network transfers. So this architecture really unlocks faster performance because you're not waiting on data movement lower latency, even at internet scale, as we can see with Perplexity, and better cost efficiency. Since compute can work directly on the local data, it reduces both the infrastructure and the operational overhead. So just as an example, if you're ranking a million products for a search query and the data and the machine learning models are on the same node, Vespa can compute those relevant scores instantly. Whereas in a traditional setup, you'd have to pull that data across the network first, which again is slower, more complex, and more expensive. So that's really why co-location is at the heart of Vespa's architecture and one of the key reasons it's able to deliver real-time AI experiences at massive scale. And you think about how much, how much data and how much storage is required for images and videos, and Vespa really enables you to process that a lot faster. Now, that leads to the low latency side. So Vespa is able to deliver the low latency responses even while processing massive data sets. So, again, whether you're ranking products, generating recommendations, or powering AI assistants, Vespa can execute those complex queries and machine learning models in milliseconds. So, and that's not just with small queries, but even when you're handling millions of documents, thousands of queries per second, or real-time signal updates, it's actually built to scale without slowing down. And naturally, that leads to Vespa's ability to handle real-time data at scale. So this is both for serving and for updating. So every write in Vespa is real time, which means you can update your data and have those changes reflected in queries immediately. So this is without batching and without waiting for index rebuilds, which is really, really great. And even better is Vespa supports true partial updates. So you can modify just the fields that you need, whether it's user behavior signals, prices, inventory levels, or ad bids. There's no need to re-index the whole document, which is great. And this really makes Vespa ideal for use cases where freshness matters. So again, think recommendations, personalization, dynamic pricing, really wanting to make sure that you're not offering up outdated content. You're not suggesting, products that are no longer available. And again, it's fast, so Vespa can handle over 100,000 field updates per second per node, which means, again, it scales effortlessly even when those signals are constantly changing. Now, a key part of advanced video retrieval, beyond just being able to scale with the amount of data, is being able to have relevant, high quality results. And so that's really, where Vespa's advanced retrieval and ranking comes in. So, when you're wanting to search within a video, you want to make sure that you're pulling the right results, the most relevant information. So let's talk about how Vespa handles retrieval and ranking. So first, in the retrieval phase, Vespa supports a wide range of capabilities. So as I've mentioned, it handles both structured and unstructured data side by side. So you are able to search across text, filters, metadata, and even embeddings all within one query. You can also use Boolean logic, filtering, and advanced operators like WAND for efficient top case search. And for vector search, Vespa supports both KNN and approximate nearest neighbor retrieval, and even multi-vector matching like token level or patch level embeddings for text and image. So what's really powerful here is that the retrieval stage is separated from the ranking stage, even though they happen on the same node where the data resides. So this really gives you that fine-grained control over performance and precision. So Vespa uses a distributed multi-stage ranking architecture. That distributed ranking, again, means that the actual scoring happens on the same nodes where the data resides, which again, this avoids the expensive network transfers. The phase ranking really lets you allocate compute more effectively and more efficiently. So you're really starting by applying the lightweight scoring early with the broader content, and then saving the heavy machine learning models for the most promising candidates. Um, and then at each stage, you can apply custom business logic or machine learn models. So depending on your use case, from personalization to content ranking. And then Vespa also supports dynamic multi-purpose ranking. So you can incorporate real-time signals like user behavior or price changes. It works seamlessly with metadata like user profiles, product attributes, or content quality scores. And you can define multiple rank profiles over the same data. So this is perfect for A/B testing, personalization, or different use cases like search and recommendations and trending feeds. So I know Zohar will talk a little bit more about this, but all of this really does add up to that flexible, scalable system to really support those high quality results, even in advanced video retrieval. Now I do want to talk a little bit more about how Vespa goes beyond vectors. And this is probably the biggest key when it comes to doing video retrieval, right? And I'll talk a little bit about why, what it is and why. So Vespa uses a flexible tensor framework to represent and process data, and this is really useful for things like embeddings, machine learning features, and ranking signals. And this really is the key to the application developed with TwelveLabs. Now, tensors are really the next stage beyond vectors. So when we talk about vectors, we know that a vector is a flat, one-dimensional array of numbers, while a tensor, on the other hand, is a multi-dimensional array of numbers, which can support multi-dimensional data. Now, you can encode different modalities into vectors, but there are some downfalls in doing that. The first downfall is you lose structure. So an image vector, for example, loses spatial relationships, like where objects are in the image. A text vector loses token level detail, like which word has what embedding. And a video vector collapses time, so there's really no way to separate frames. You also can't combine modalities cleanly through just vectors. So if you want to search across text, images, and video and compare them meaningfully, you really need a way to represent and align those different modalities. So this is where tensors come in. Tensors allow you to store those token or patch level embeddings, those per modality dimensions, and metadata like timestamps, bounding boxes, or modality type. Vectors alone can't represent those relationships because they're flat. And advanced retrieval methods like video retrieval, they really do need more than vectors. So when we talk about techniques like Colbert or Colpoly, which Colbert's the late interaction of text token embeddings, and Colpoly's the multimodal retrieval using polygemma. They need multidimensional tensors to store multiple embeddings per document and interact with queries in a fine-grained way. So this is really why, again, a vector database alone isn't sufficient, because without a tensor framework, you'd have to hack this together manually and it won't scale. So when we think about tensors, we're really thinking about better multimodal representation, interaction, and scalabilities. And tensors really give you flexibility and structure, compatibility with multiple data types, and fine-grained retrieval across modalities. So again, when we think about multimodal retrieval, tensors play a key role in being able to do that efficiently with better context and at a higher quality. So with my last slide, I want to talk a little bit about these emerging technologies. We know that AI is changing rapidly. We've seen a lot of evolution within the last year or two, from agents and foundation models to vision language systems. And there really is a need for that scalable, production-ready platform. So, just as a final note to share that Vespa has been built from the ground up to power those real world AI applications, not just experiments. And one of those key examples is how Vespa supports vision language models and other multimodal AI. And this is really thanks to its advanced tensor framework. And Vespa can handle those complex embeddings at scale, which enables the powerful search and retrieval across text, images, video, and more. So this really opens the door to richer, more nuanced AI experiences. And when we think about, Vespa's support, it doesn't just support today's model, but it's also future-proof platform. The flexible tensor computation framework really allows you to express any inference or scoring logic over your data. So that makes it easy to integrate the latest breakthroughs in machine learning and AI as they emerge. So, I guess to summarize, Vespa positions you to not only build with today's AI, but to scale and evolve with the next generation of models, modalities, and agentic workflows, not just to experiment, but to deploy, scale, and deliver real value in production. So, with that, I'm going to pass it over to Zohar to really talk through a little bit more detail in how we're able to do this video retrieval at scale with TwelveLabs. Zohar?
Yeah, thanks, Bonnie. First slide here. So, as an introduction, right, like to set the context, as James mentioned, Vespa and TwelveLabs have partnered to develop some assets around this. What was the motivation for Vespa really is that we went to around late last year to a couple of AI conferences where, after explaining what Vespa was, some prospects from came with enterprise use case about, hey, can you guys help us with video retrieval? Your tensor framework and your platform seems super powerful. So, a couple of cases that stuck out to me was, there was a large Fortune 100 company, 100 company who wanted to essentially have some sort of an AI assistant which would help their services team to be able to very quickly find out on how to do a given procedure that's probably explained within 10 seconds of hundreds of training videos on how to different things, right? Like it could be customer support, it could be field teams, being sent on the field. So they needed really to retrieve chunks of videos very quickly to show them how to do certain things, right? Second use case that came up to our booth was, hey, you know what? All the financial news, right? They need to be multimodal as well, right? So it's great to automatically absorb news feed and textual information mostly to be able to give a summary of what's happening with a given company and stock, but they also wanted to be able to retrieve, any segment of the news, any, CEO interviews about a statement that he might have given about any stock, and just precisely knowing, okay, this is the section of the video where he talks about the stock of his company and the growth prospect and whatnot. I think the end client in this case was some brokerage firm, right? So these use cases seem very powerful to me, but we didn't for Vespa, as long as you have a very powerful embedding model, then we can make it work, right? So the two questions I came back with from the conference is, how can we do this? Where can I find the embedding model, right, to be able to do this? And then how can I ensure high quality retrieval to be able to do a very contextualized search, which is not only based on, on the embeddings of the video, and how do we do it at scale, right? And that's how we came across TwelveLabs, and for us, like, it was essentially a match made in heaven, right? Because TwelveLabs really provides us some state-of-the-art advanced visual language model, which are really designed for industry-grade video understanding and processing. There's two models that we used as part of this asset, right? The first one is a video understanding model, which is capable of generating information about those videos, right? Like you can enable with Pegasus 1.2, you can enable tasks like summarization, metadata creation, detailed reporting. That sounds great, right? Like any piece of video needs to have some metadata associated to it. And Marengo retrieval which is the SOTA model for the actual embeddings of the video. And these are like contextualized embedding, which enable this high quality retrieval, right? On the other side, you have the Vespa platform, whose design point is scalability, low latency, our flexible tensor model that Bonnie touched upon, and our fine-tuned, customizable and advanced ranking, and the ability to do hybrid queries. Next slide. So the first question that comes is, in Vespa, everything is every piece of information is a document, right? So you see here a video, right? Like, so how do we model a video document in Vespa? Typically, you model the document based, obviously, on the data that you have, but also the question that you want to ask to these documents, right? So in this case, what I implemented was, okay, any video has a URL, right, where it can be accessed. But then we want to represent, the title of the video, which is obviously an important piece. The keywords, right? Some keywords associated to what's in that video, right? That enables some level of search, right? And a video summary, right? Like, what's the abstract? What's the story of that video, right? So if you roll back to the blockbuster times, that's how people used to choose which movie they want to borrow, right? They look at some sort of metadata before picking up that VHS tape, right? And finally, once we have the metadata, we want to have obviously the embedding. So why do we want to do that, right? The reason was essentially to do this optimally in terms of high quality retrieval, because any search is going to be contextualized, right? Like when, for example, you are looking for a scene where a cowboy is riding into the sunset, well, maybe if you just do it based on the embeddings, you're gonna get, some scenes from some documentary on the cowboy's lifestyle. But what if you're looking for, hey, I'm looking for a cowboy riding into a sunset in a Western flick which has some romance in it, right? So here you provide an entire context, and some of the metadata, like the summary of the video, the keyword, the title, might have this as part of the lexical. So it might already help you in a first phase to be able to isolate, okay, these are all the Western flicks I have, and maybe this is where I need to look for a scene where there's an actual cowboy riding into the sunset, right? So that's the kind of idea behind the way this document is modeled. So it's enabled that contextualized search. It also kind of optimizes your storage, right? So instead of storing each of your embeddings segments, because actually the Marengo model chunks the video by default into 6-second chunks. And if you store them separately, you need to associate some piece of context and metadata to each document. Instead, what we've done here, as a header of the document, we are storing all the metadata, and the rest of the information, like the chunks of the video, the start and offsets, and the embeddings themselves are stored in an actual multi-vector structure, because a Vespa, given its flexible tensor model, allows you to do that, right? So now we are optimizing storage. We are enabling this for high-quality retrieval, but you will also see in the next slide how this enables us for very fast retrieval with an optimized ranking. Next slide. So in terms of ranking, right? The way we're going to do this is, let's say I retrieve my set of Western videos, and the first phase can be computationally lighter because I might have millions of videos, right? So here what I'm doing, I'm just doing a lexical search based on BM to best match 25, which is a scoring technique for lexical, on the title, keywords, and the summary, right? And once I've retrieved maybe the top K matches, then in order to make the ranking computationally less expensive, I will only rank the different chunks and segments of the video in a second phase, right? So this allows me to scale. This allows me to, really quickly isolate in millisecond response time out of millions of video, be able to isolate the top matches. Next slide. Finally, querying the videos, right? So now I've stored my video in that document model. I've defined a ranking strategy which is scalable, and now I want to query. So Vespa enables you for hybrid queries, like Bonnie was telling you. Within the same query, I could have some structured attribute. In this particular example, I don't, but it's very easy to imagine where I could have a structured attribute based on the publish date of the video. Like I want any videos past 1982, for example, right? As a year of publication. And here I'm doing it within the same query, I'm doing a lexical search with the term user query. In this case, I'm looking for a scene where there's a Santa Claus on his sleigh, right? So I'm going to do a lexical search across the title, the keyword, the summary, to kind of retrieve what is the set of the video which might have, this kind of scene within it, right? And I'm also doing an ANN search now by embedding these query terms using the Marengo retrieval model and retrieving the top segments and the video chunks where this appears, right? And you can see here I specify the ranking model. I could have hundreds of different ranking strategies. And in this example, obviously, we have only implemented once, but this kind of makes you realize how precisely you could do queries by even being able to specify your ranking strategy within the query, right? So this query essentially will do the best lexical match based on the user query term, and also ANN search for the top 10 segments by comparing the query term embedding along with the actual video embedding. Next slide. So now it's time for the demo. Just doing a time check here, James. How long do I have?
You still got like 20 minutes, so feel free to take your time.
Okay, perfect. Yeah, so that's good. That's what I needed. So let me, Bonnie, if you can stop sharing. Okay. Are you able to see my screen?
Yep, you can see
The
it.
notebook?
Yes.
Okay, perfect. Yeah. So this asset was developed as a notebook, right? And we have provided all the links here. I will paste it into the chat later for this video for this asset. It's comprehensive. The notebook end to end will help you deploy the entire Vespa cluster, feed the document, and start querying the document, right? So the use case that we've taken here is some cartoons from the Internet Archive Library. I was looking for short animation so that, it doesn't consume a lot of embeddings, and I want to be cognizant of the amount of credits that you get with the TwelveLabs API. So it works super well. It shouldn't consume a lot of your credits to be able to run this, right? So the use case is I want to retrieve some scenes across these three cartoons for Santa Claus on his sleigh, right? And I'm going to walk you through this notebook here. So it's Python 3.11 or plus will work. You have to install a few libraries, Vespa and TwelveLabs, pandas for some user consumability of some of the output coming from Vespa. I'll just skip this. One of the prerequisites is to get a TwelveLabs API key. So you can sign up on this link and get your API key, which will give you a 600 minutes of video. And you also have to sign up for a Vespa trial account. The link is given here. You will get $300 free credits, which will be more than enough to play with this use case for a few days. One thing that you do need is a tenant name that you create when you spin up your trial environment. and your application. So you need to give a name to your application. In this case, it's called video search. And the first step, so the 3 videos I've chosen are really this one, right? So let me show you actually in the index detail. There is a Christmas cartoon that is 24 minutes, in length. Some random animation video of a worm, trying to get into an apple. And you probably might recognize this one. This is coming from Ice Age, where you have that squirrel, which is causing the end of the world with his acorn. So these are the 3 videos I'm using as a sample. And they're passed here as URL, right? So the first thing we need to do is to create, so the first step is to actually generate the metadata regarding the video, right? That we're gonna pass as part of the document. So there are a few steps. You need to create the index, upload the videos, and then you are kind of ready to generate the metadata. So as you can see here, we are using the Pegasus model, and we are passing as a prompt, hey, I want to summary. So we can pass a prompt, generate an abstract of the video, serving as metadata on the video up to 5 sentences. So we kind of want to limit it. And the second one is I want to generate 5 keywords, right? So when you run this, you kind of use the TwelveLabs Pegasus model to be able to get this done, right? And what this generates for you is, for the 3 videos that I showed you earlier, it's going to generate you a nice summary and the keywords. So that's the only piece of metadata that I needed. The titles were there as well, but the titles was provided from the Internet Archive. That's a piece that I brought over, so no need to use Pegasus for that. I could have asked the model to give me a title for the video as well, but these are the official title of these 3 cartoons that you see. Now that we've generated, the metadata that I have, or kind of given it to my notebook, right? What is the URL of the video? What is the title? This came along from the original Internet Archive site. And now I also have, a nice summary and the keywords to refer to these videos, right? So the first step here is to, now I'm ready to actually generate the embeddings, right? So in order to generate the embeddings, I use the Marengo retrieval model, as you can see here. And sequentially, what I'm doing is that I'm generating the embeddings for the 3 videos, right? It does take a few minutes when you run it. Here, in the interest of time, I'm skipping this part. And finally, once it's ready, we can retrieve the video. We can retrieve the embedding. So I already had the task ID, and based on that, I did a live query to retrieve these embeddings. And now I'm gonna go step by step, right? So here, first thing first, right? When you take the Marengo model, the first information that I was curious about, okay, what do I get as an output of the embedding model? So what you're gonna get as an output of the Marengo model, in the way it's being used here, is that it's gonna chunk your video by default in 6-second segments, right? And that is entirely, you can actually parameterize this. You can use smaller or larger chunks. It's gonna give you an embedding scope that this is a clip of a video. And then for each of the chunks, it's gonna give you, as you can see here, a vector of size 1024, okay? And this is made of, arrays, right? So here I have essentially, for each one of the video, I have just displayed what the first segment looked like. So the first video has 6 segments, so that's a 36 seconds video. The second one has 242 segments. That's around the 22, 23 minutes video. And the last one is a 24 seconds video, right? So now I've got, 4 chunks with 4 segments, 242 chunks with 242 segments, and so forth, right? Now I've got everything that I need. I've embedded my video contents by chunks. I've generated my metadata. I've got, and now I'm ready to essentially deploy a Vespa application and feed all this data to Vespa, right? So the first step is essentially to create an application package. An application package contains the schema, the topology of your cluster that's going to require to be handled that application. So at the very minimum, it's a services.xml, which contains your cluster definition and the schema. In this case, for services XML, we are just using the default, so we don't even have to provide that. We are just specifying the schema. And you can see here, it's what you saw early on the slide. We have the title on which we enable BM25 index so that you can do lexical search on it. You have the keywords, right? So the keywords are generated here using the Pegasus model. You have the summary that I showed you earlier, which is going to be ingested. And then you have the embedding scope. So the embedding scope is generated one per array, per chunks. And since it was always a clip, I just, created one field saying that this is a clip, right? Versus a piece of audio, whatever, and storing it as a sort of metadata piece. And then you have essentially your all the video embedding chunks, right? So as part of this, you have the start offset, the end offset, which is stored in an array of float, and your actual embeddings, which are stored as a mapped vector. So there's an identifier for the number of chunk and the actual vector, right? That's the flexibility that Vespa gives you in representing your multi-vector structure, right? And we are creating an HNSW index to be able to do a cosine similarity search. And here I've defined my my ranking strategy, right? So first phase, I want just to do a lexical phase, lexical based ranking based on BM25 of the title, keyword, summary. And in a second phase, I actually want to do a cosine similarity search on my query terms on each segment versus the query terms. And that's basically it. At this point, I'm ready to deploy my application package. So here with package, I kind of create the application package, and I'm ready to deploy the application. So I want to see what this, I want to show you what this looks like on your Vespa trial account, right? So once you deploy the application package, this is what you will see. You will see your 3 documents. That's after feeding, you will see 3 documents. And at the minimum, you will see your Vespa cluster with one content node, right? So very small environment with 2 cores, 16 gig of memory. All of this was deployed just through the notebook, right? And a stateless container node which manages the ingress into that cluster, right? So that's what your Vespa Cloud Console will look like. What you also get, by the way, is an endpoint, right? So this is how I'm going to communicate with this endpoint to feed the cluster and to be able to run queries on it. So now I deploy the application, and now I can feed. I prepare the feed for the application, right? So preparing the feed in Vespa, you require a structure which requires a document ID. So here the ID is generated using a hash lib, right, between the URL and the index ID that for that given document, just to give me make sure I get a random unique value. And then the document itself is going to be made of a nested JSON L with the ID of the document and a bunch of fields, right? So the URL, title, keyword, summary, the starting offset, and the embeddings. And at the end, for each video, I will create 1 document. So 3 documents are created. So let's see what this looks like. Here is the first document, which is the video called the end. This is the URL of the document, the title, the keywords, the summary, the embedding scope, and then the start offset are stored in an array, the end offset are stored in an array, And this is my multi-vector map structure. So I have an identifier of that vector, positional, and then I have my vector made out of 1024 values. Just for readability, I just truncated the display to the first 3 values, right? So that's basically what each one of my documents will look like. I'm going to skip the feeding process. And now let's do a hybrid search on the video, right? So I'm looking for Santa Claus on his sleigh. So in order to be able to do an ANN search, I need to embed this query term, right? So let's use the Marengo model to embed that. And I will get, as an output, my array, my vector made of 1024 float numbers. And I'm ready to essentially run my query that you saw on the slide, right? So what I'm doing here, again, is I'm doing at the same time a hybrid search, which is performing a lexical search on the metadata, on the textual information related to the video, as well as an ANN search on all the segments to be able to retrieve the top 1 hit, right? So you can see hits here has been set to 1. I pass as an input parameter my string of the user query, and I also pass the query embeddings that I generated earlier. And this is the answer that is returned from Vespa, right? So it's actually the entire document. So you are asking for the top hits. Oh, surprise, the video that has been retrieved was, towards the night before Christmas. This is where I will likely have a Santa on his sleigh, right? And one piece of information interesting here is that it retrieved the video based on the maximum similarity score of a segment across all videos. So if you take all the different chunks and you calculate the similarity score versus the query term, this chunk number 212 in this video is the highest scoring across your sample of videos. So if we take a look at this, so these are my offset, right? Start offset and offset. And these are my similarity score later on calculated. This score is the maxim between the query embeddings and the embeddings of that particular chunk. So this is telling us essentially that if you're looking for Santa of a sleigh, it's going to be in this chunk. And you can kind of visually see, yes, it is the highest value, right? So now you kind of need some help to digest this information. So this is where I'm using a bit of Panda to make it more digestible. And you can see what I do here is that I traverse all the chunks of that video and I retrieve the top 10 similarity score matching, right? So essentially this tells me that the chunk number 212 has this similarity score, and this is the starting offset of 1272 seconds up to 1278 seconds in the video, and so forth for all the chunks. One thing to notice is that some of these chunks are contiguous, right? So it might be one scene, and that Santa Claus on his sleigh video might be across multiple chunks. So there's one more thing we can do is we can still use the magic of Python to further refine those results and give me the concatenated segment converted in minutes and seconds, right? So at the end, these are my top 3 sort of sections of the video where I might see a Santa on his sleigh, right? So let's spin up a player and review the segment of interest. By the way, these are no longer ranked by relevance. These are ranked by chronological order in the video, but the segment 212 belongs in that chunk. So let's first see this one, right? 2039 to 2121. So 2039.
Gave the luster of midday to objects below. And what to my wondering eye should appear but a miniature sleigh and 8 tiny reindeer, with a little old driver so lively and quick, I knew in a moment it must be St. Nick. More rapid than eagles his coursers they came, and he whistled and shouted and called them by name.
By the way, I developed this notebook during Christmas. That's why the video is related to Santa honestly. So you get the idea, and with the power of TwelveLabs, and Vespa here, you can kind of see how both solution enables you to do this at scale, across millions of videos, and not lose on latency, not lose on precision, and being able to do, very much contextualized search. So I think that's it for the demo.
Yes. Is that the end of the presentation?
Yes.
Awesome. Well, thanks a lot, guys. I really appreciate you walking over the there's a lot to uncover, but I think that the demo is great, and it showcases real world examples of how it works. It'd be great if you can also put the link to the Colab notebook and the Zohar blog tutorials and the repo to the chart as well. Maybe even like show it on the screen again, because I think there'll be folks who watch this recording later on, and they can
So here it is.
Discover them afterwards. We have about like a couple minutes left. Is there any live question from the audience? Feel free to just unmute yourself and ask it. So, maybe one question that I have is just around that concept of tensors, right? I think there's Bonnie have a slide on tensors, and that I think you mentioned that is like the next evolution of vectors, right? Is there any like materials content?
Yeah, absolutely. I can share a document there.
Yeah.
Let's grab the link here.
No worries. And yeah.
While Bonnie is retrieving that, I put all the links, the two blogs and the actual notebook. So you should be able to have from there all the links you need to run this by yourself.
Maybe one question from like the customer like production use cases, right? I think there's this couple slide on anything around like consumer application and Ethernet enterprise use cases that could be very suitable for using Vespa platform. And I think that Zohar, in your first slide that you mentioned in the context of video, there's two ideas, right? First one is like financial news, where you can use video to ask questions around financial information, and the second was around, I believe, was like training videos, right, where you can extract summaries, content. It's curious. What are some of the like real world examples of custom use cases that potentially leverage video that I think Vespa is most excited about.
I think so far for us, these are starting to come, right? These use cases. These are the two examples that I had in mind right now in multimodal AI, but we are expecting to see more and more, right? Like in terms of multimodal, as you understand, Vespa is an agent, like that is the perfect platform to serve as an information retrieval for agentic AI, right? So in that sense, if you want your AI agent to be even able to retrieve information from, like it could be enterprise search use case, right? Like you have tons of conference calls, you have tons of training videos, having retrieval modality to be able to go and look for certain pieces of information directly in videos is essentially going to be a very powerful case, right? Instead of having to scramble manually by just looking for conference call dates and whatnot, right?
Yeah, for sure. Those are like super exciting, and We'd love to collaborate with the Vespa team more on perhaps them building like some sort of sample application on top of the notebook that you created, right? Like where we have like a complete like a front-end interface that that target end users, right? So basically building on top of the notebook and the repo that you already built, that is more for developers, but I'm sure like to attract like end users, you need like more complex front end to demonstrate like our integration.
Yeah, certainly, yes. Makes sense.
Yeah. All right, I know we are running, I think folks start leaving the webinar now. So thanks again, Bonnie and Zohar, for spending time preparing for the slide today. Extremely comprehensive materials, and the recording of this session should be available on YouTube probably in the next couple of days, and be sure that with you guys so we can socialize that within Vespa as well. And yeah, super excited about like our continued partnerships and more our product integration, application, and marketing / community events that we can collaborate in the future.
Yeah, thank you so much.
Thank you for having us, James. Appreciate the opportunity.
Yeah.
Thanks, guys.
All right. Bye.
Bye-bye.